Hello, it's time to exploit inverse function now. So we have understood what inverse function is. My videos on part A and other videos on inverse function gets into details of inverse function. Here we'll try to exploit our knowledge of inverse function and take some unique examples. I know in many times in books they write that the domain and range flips for function and its inverse, but they give examples like a line, right? So in a line, inverse of a line is also a line, and both have domain all real numbers, range all real numbers. So even if they flip, how does it matter? It's still the same. So let's come out with some unique, very beautiful examples, and I will show you the very first taking line itself. But my line this time is going to be slightly different from what you normally see. We'll take a line which is horizontal. Well, this line is a function, correct? For every value of x, we have a unique value of y. So, and let's say, now we'll draw a line which is y equals to x. Let's say this line is y equals to x. And let's say this is my line y equals to 3. In that case, what is going to be the inverse of this line? Well, what is this point? Y-intercept. The value at this point is, or the coordinates at this point is 0, 3, correct? What should be the value here? Line is 3 and it intersects y equals to x. So of course, this point is 3, 3, correct? Now the inverse of this, coordinates will flip. So when 3, 3 flips, we get the same point. And when 0, 3 flips, we get a point which is kind of here, which is 3, 0, right? 3, 0, 0, 3, 3, 0 on the inverse function. Therefore, our inverse function would look like what? The horizontal line gets transformed into a vertical line. Do you see that? Vertical line. So we get a vertical line out of it. So the equation of inverse function here is x equals to 3. See, what was our function? Here, fx was equal to, we could write in terms of fx equals to 3. Now to find inverse, we convert this to y equals to 3, and to find inverse, what we do for this first step, and then we flip x and y. No x here. So just replace y with x and we get what? X equals to 3. And we say f inverse of x is equal to 3. Thus, so our horizontal line gets transformed into a vertical line when we find its inverse. Now see the beauty of the example. What is the domain of our function? Domain is x belongs to real numbers, correct? And how about range? Y equals to just 3. Now when you flip it and you get f inverse x, so what is the domain and range of f inverse x? They flip, right? You see that. What is the domain? Just the values? 3. Do you see? The domain of inverse function is x equals to 3. And the range is y belongs to real numbers. All numbers along this line. Beautiful example. So here we understand how the points interchange, how x intercept changes to y-intercept, and how domain and range changes. Do you see that? Very simple. Now, many books give another example, which I'll give it here for the time being. This is y equals to x squared. So let me draw in red all our functions, okay? So this is our x squared function, correct? Now, if I have to draw inverse of this, we'll see a line y equals to x. Here what we did was, we just for the time being, okay, let me draw the full function. Y equals to x square has the domain of all real numbers, correct? So in minus side, it will be symmetric about y-axis, and that's how we get it. And to flip it, we get our inverse, right? So our inverse look like this, which is like y equals to plus square root x and y equals to minus square root x. This particular example of function and its inverse is very beautiful to demonstrate that how we can limit the domain of the function so that we get inverse also as a function. Here, as you can see, the function fails horizontal line test, correct? If I draw a horizontal line like this here, it cuts at 2 points, and therefore the inverse fails vertical line test, and inverse is not a function. Yes, it is not, because y equals to x square. When you flip to find the inverse, then you write x equals to y square and y equals to square root of x. Whenever you do that, you do plus and minus. For each value of x, we have two values of y. Yes. So it is not a function. Well, so what we can do is we can restrict domain in this case. Well, if we say restrict domain for x greater than or equal to 0, in that case, we are only considering one half of our function. And for that half, when we do the inverse, we get the upper limit, right? If we construct this, then we get this. Now, because we are not looking into the other half, the inverse of this function is a function. So, restricting domain can ensure that the inverse is also a function. Okay? That's a very beautiful example to show that particular aspect of inverse being a function also for a function. Okay? So as you can see, it is not necessary that every function's inverse will also be a function, right? As in this case, it is not a function, but we restricted our domain to get a function as an inverse also, right? Now, let me take the very exciting example now. This is 2 to the power of x. This is one of our parent function, the exponential function, correct? We don't really deal much with this function in grade 11, but in grade 12, we work into exponential function, and we know inverse of an exponential function is a logarithmic function. Well, at grade 11, we are not really aware of logarithmic function. So, we can't even calculate the values. How will you find inverse of such a function? That is exploiting inverse function by flipping the coordinates, correct? Let's do it. So what we will do is, now we will see here, concentrate here. Now here we will just plot some values and see what happens. So let me make a table of values here for you. And we are considering the function fx equals to 2 to the power of x, correct? So we'll have some values of x and then calculate 2 to the power of x, correct? You know what is 2 to the power of 3? 2 times 2 times 2, which is 8. What is 2 to the power of minus 1? 1 over 2. And 2 to the power of minus 2 is 1 over 2 times 1 over 2, which is 1 over 4, correct? So now let's plot some values. Let's start with, let's say 0. 0 is a good point to start with. 0. So what is 2 to the power of 0? Many students get this wrong. 2 to the power of 0. I've listened to so many answers like 0, 2, 1. Well, anything to the power of 0 is just the number 1. Okay? Why? I'm not getting into that detail now, but you should know anything to the power of 0 is just 1. Now, let's take 2 to the power of 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 times 2 times 2. Correct? Like that. Now let's look into the negative values. Minus 1. So 2 to the power of minus 1 is half, right? 1 over 2. Correct? Minus 2. 2 to the power of minus 2 is 1 over 4. Correct? That was 4. 1 over 4. 2 to the power of minus 3 will be 1 over 8. Is it okay? So like this, we see as the number increases on the negative side, we come to a smaller and smaller value. On the other hand, as the number increases on the positive side, we get bigger and bigger values. Right? For example, if I say number 10, then 2 to the power of 10 is kilobytes, 1024. A huge number, 1000, around 1000. Do you see that? Here, if we do 2 to the power of minus 10, then it will be equal to 1 over 1024. Do you understand? Approximately 0.0001, such a small number. So, as we go on the negative side, our values decreases and approaches 0, correct? They approach 0, correct? So, when you are approaching 0, what happens? You are approaching a line x-axis, y equals to 0. So that becomes your horizontal asymptote. So this is also a unique function amongst our parent function which has a horizontal asymptote. Yes, I know. Reciprocal function also has it. Reciprocal has both horizontal and vertical. This function has just horizontal asymptote. As you can see, if we go on the higher side, the values increase indefinitely, like very, very high. So it approaches to infinity. So let me write that. As we approach, this is the end behavior part. As we approach negative infinity, very high value, here we approach 0, the y value. And as we approach positive infinity, we approach, the function value approaches infinity. Correct? Now let me plot some of these values and get our function here. Okay. Now, I should have actually drawn this line slightly higher. Let me do it now. It's not too late. It's not too late. Let me do it now. Because I need the lower half of the graph also. Okay, let's see. So we are just shifting our x-axis for the time being, making a correction. It's not a bad idea to do corrections at the right time. Okay, so now this is our x-axis. That's our y-axis, okay? And that's the origin, 0. Let me write down this 0 here. Let's put the points in. Correct. So let's start with 0. At 0, 2 to the power of 0, 1. So the first point which we get is here, correct? And at 1, we get 2. So at 1, the value is 2. At 2, the value is 4. At 2, the value is 2 plus 2, 4. At 3, it is 8. So 1, 2, 3, and we get 4 here, 1, 2, 3, 4 here, 8. Oh, we need not go further. That's okay. Now the minus side. At minus 1, we have 1 over 2, which is half. At minus 2, 1 over 4, half of that. At 3, minus, even half of this. And 4, even half of that. So we are coming closer and closer to x-axis. So we say, as we go on this side, let me draw this now. We are approaching 0. And on this side, see how rapidly the graph grows. So that's the graph for 2 to the power of x. Correct. Now, let me draw the line. You know which line? Y equals to x. Why am I drawing this line? Because we want to exploit the inverse function. And inverse function is all about reflection on the line y equals to x, correct? So that's what we will do. That's the line. And this line is y equals to x, correct? To draw the inverse of a function, you have to just flip the points, correct? So I don't know that inverse of 2 to the power of x will be log to the base 2x. Oh my god. I don't want to know that. But with the properties of inverse function, I can draw that graph. Okay. How? This point will go, it is getting reflected on y equals to x. So it half and half, it gets reflected here. Do you see that? This point, where will this come? And this was y-intercept. Y-intercept became x-intercept. Did you see that? So nice. And here, half and half. There you are. Here, 1 and 1. There you are. So let's take this. 1, 2 and a half. Half, 1, 2. There you are. So we got all our graph points on the first quadrant. Okay. Let's look into this place. Now here, kind of dicey, right? This point is not so good. And this point, oh my god. So this is like slightly more than 1, right? Slightly more than 1. Let me put it here. Because these points are like fractions and fractions. This is slightly more than this. Let me put it. But the important thing is, when you are approaching minus infinity for x, you are approaching 0. So when you flip, that means as you approach 0, you approach minus infinity. Do you understand that part? So basically, on this side, you approach minus infinity. Do you see that? And on this side, we flipped all the points, and so we have a beautiful graph here. This is f inverse of our function fx, where what is fx? Fx is equal to 2 to the power of x. Now see, we have inverse of our function right there. We could draw the inverse of the function without even knowing the algebra part of it or the calculations part of it, using the information which we have learned in inverse of a function, right? Scientists really took a lot of time to discover this function. Anyway, now let's look into the properties. First, you've already seen the domain. What is the domain of this function? For the red function, the domain is x belongs to real numbers, correct? And the range is y belongs to real numbers and y is greater than 0, never equal to 0. Why? Because this becomes an horizontal asymptote. What is an horizontal asymptote? It's a line which we approach. We never really reach there. We just approach. So that line is x-axis, and the equation of that horizontal asymptote is y equals to 0. Correct? Now here, what happens to the domain? Domain is just, greater than 0. Do you see that value? X belongs to real number, but x is greater than 0. It is never equal to 0. And how about range? Range is all real numbers. Do you see that? Y belongs to real number. Do you see that? So that's how we can show how domain flips to range, how the points interchange. Do you see that? This point, 2, 1, 2, 3, 4. This point is 2 and 4. And where did it go? 1, 2, 3, 4 and 2. Do you see that? See how the points flip. Similarly, all the points flip and we get our beautiful inverse function. So, one of the best examples which you can really draw, graph or sketch and understand inverse function is probably the exponential function. Here, there is a restriction on domain and there is a restriction on range, and both are different kinds of restrictions. So when they flip, you really appreciate it. Secondly, you get a function which you never knew about. Do you see that? So that's how it is. Okay, I hope you liked and appreciated the effort. Here, do we have a horizontal asymptote? No. What do we have? We have a vertical asymptote. And what is the equation of vertical asymptote? It is approaching which axis? Y-axis. The equation is x equals to 0. Do you see how the horizontal and vertical asymptotes flipped? they also flip. So horizontal asymptotes becomes vertical asymptotes, and the equations also. Y equals to 0 changes to x equals to 0. Okay? That's interesting. I hope you enjoyed this lecture and also recalled all the properties of inverse function while doing this. Okay? Thanks a lot. Have a good day.